We're continuing physical chemistry now. We're in chapter 19 still. We're beginning section 4. We're going to talk about angular momentum now. For angular momentum, of course, we're going to do two approaches. First, we're going to review the classical approach. Now, this diagram is kind of a mess, and you have to think of it three-dimensionally. So we have our x, y, and z three-dimensional space, just like we had before. And we have a mass out here. It's a certain distance from the origin. So that distance is r for radius, of course. Now, this mass, because of its angular momentum, it's moving. So it's got linear momentum. We're using rho or lowercase p for linear momentum. So this radius and this angular momentum, because it's going around in circles, this is the center of the rotation, they're going to be perpendicular to each other. But anyway, so then so p is linear momentum. So this linear momentum, of course, this little arrow means it's a vector. So that's mass times velocity. And again, this little arrow over the v makes it a vector. And of course, m is mass and v, well, without the arrow it would be speed, but with the arrow it would be velocity. So we're using capital L for the angular momentum. The angular momentum is this other vector. It's perpendicular to both r and to p. So the magnitude of this vector L, the absolute value of L, is going to be r, this distance, times p, this distance, times the sign between them. I made a mistake when I said they were perpendicular. They're not necessarily perpendicular. So whatever angle is between radius and the linear momentum, you take the sine of that angle. Obviously, we'll normally do it in radians. So then for the right-hand rule, remember if you have your, let's see, r and then p, your L is going to come out this way. So in our case, we have r and then p, so our L would be sticking out this way. That's the right-hand rule. So remember, hopefully you've already learned what cross product or vector product is. So we're defining the angular momentum as the cross product of this radius times this angular momentum. Both of these are vectors, of course. Obviously you can't do cross product on a scalar. So remember what I said before, r and p, they're not necessarily perpendicular. But L, the angular momentum, is perpendicular to both. I already said that, but this is another way of writing the same thing. The vector for the angular momentum is perpendicular to the vector of the linear momentum, and of course the vector for the angular momentum is perpendicular to the vector for the radius. Continuing on physical chemistry, chapter 19, we're in section 4. So we just did a review of angular momentum from classical mechanics. Now we're talking about quantum mechanics. Now in quantum mechanics, there's actually two kinds of angular momentum. The first kind is the orbital angular momentum. So in other words, for any electron and electron orbital, just by being in that orbital, it's going to have some angular momentum. So this will be different for each orbital. And this is analogous to the classical picture that we just reviewed on the previous slide, except the computations might be different, of course. And then the second one is what we call intrinsic or spin angular momentum. Now this is something that just belongs to the particle and there is no classical counterpart. So don't try to visualize what it looks like, just do the math and not worry about what it means. So this is going to give us a fourth quantum number. So here's an example of a problem we've got to solve for the angular momentum. So we have L hat, so this is going to be our operator for the angular momentum squared of psi of ml, oh that should be n, n, l, and m. So this psi is a function of the first three quantum numbers, and then that's equal to L times L plus 1 times h bar squared times psi of nlm. So this is an eigenvalue problem. Our psi, of course, is the eigenfunction, and then this over here, this is our eigenvalue. So the absolute value of L, that's going to be our orbital angular momentum, which obviously means it's going to be always positive or zero, non-negative, real. So to calculate it, absolute value of L is equal to the square root of lowercase l times lowercase l plus 1. So L is a quantum number for angular momentum. So as an example, for S states, L equals 0, P states, L equals 1, and then D states, L equals 2, and so on. So there's going to be a component, x, y, z. So like L for z is going to just be mass times m, not mass, quantum number m. So this m is going to be the z component of L. We'll talk about that in a little bit. Continuing on physical chemistry, chapter 19, we're section 4 still. So we're still talking about the orbital angular momentum. So for an S state, or an S shell, lowercase l, or the quantum number, is going to be equal to 0. So the absolute value of L, or the magnitude of the angular momentum, is 0. And therefore the z component of L is going to be 0. Now for P shells, P orbitals, P states, whatever you want to call it, lowercase l is equal to 1. So using that formula I showed you before, the angular momentum absolute value is going to be rad 2 h bar, square root of 2 times h bar. Remember, h bar is Planck's constant divided by 2 pi. Now the z component, remember, it depends on the other quantum numbers, m, lowercase m. So it could be minus 1, it could be 0, or it could be 1. Therefore, the z component of the angular momentum will be either minus h bar, 0, or h bar. So this is what it looks like. Here's our z component to the angular momentum. And if m is equal to 0, then there will be no z component to the angular momentum. So all the angular momentum will be in the xy plane. But if m is positive 1 or lowercase 1, then you're going to have this part of the spin angular momentum, or orbital angular momentum, in the z axis, and that's going to be equal to rad 2 h bar. Now remember, you got to think three-dimensionally here. This is not a line, it's actually a cone that goes 360 degrees all the way around the z-axis here. And then for D states, lowercase l is equal to 2. So the absolute value of L, the magnitude of your angular momentum, is going to be, remember, square root of 2 times 2 plus 1 h bar. So we simplify that, it's just going to be rad 6 h bar. So now we have 5 different possibilities for what the z component of the spin angular momentum will be. M could be 0, 1, 2, minus 1, or minus 2. So we'll have either 0 z component of the angular momentum, or, oops, I didn't find the length of this vector. But anyway, whatever the length of these vectors are here, that's how much of the angular momentum is going to be in the z-axis. Continuing on physical chemistry, chapter 19, we're finishing up section 4 now. So, let's see, the angular momentum operator squared of psi of NLM is equal to L times L plus 1 times h bar squared times psi of NLM. That's for the whole angular momentum. Remember, we're talking about the orbital angular momentum. Then the z component, we have an operator just for that, so the same thing. The L hat for z of psi of NLM is equal to m times h bar times sine of NLM. And then, again, the Pythagorean theorem says the L hat operator squared is equal to the L hat operator for x squared plus the L hat operator for y squared plus the L hat operator for z squared. That's just the Pythagorean theorem twice. So for an example, just for x, we have the L hat operator for x, that's minus I, remember I is the square root of negative 1, times h bar, times the entire quantity, y times the derivative with respect to z, minus z times the derivative with respect to y. Now L hat squared, now notice we replaced h bar with h over 2 pi. So we have minus h squared over 4 pi squared times this entire thing. 1 over sine of theta times the derivative with respect to theta of sine theta times the derivative with respect to theta, plus 1 over sine squared theta times the second derivative with respect to phi squared. Now, believe it or not, that because this is in spherical coordinates, obviously, we're talking about angular momentum, so that's easier form than the Cartesian equivalent. Continuing on physical chemistry, chapter 19, we're going backwards to section 19.3 now. So the wave functions, we're talking about the wave functions of a degenerate energy level. Remember, degenerate energy level is when you have more than one function that have the exact same energy. So let's say that we have energy level 1, but two different functions have that same energy level, psi 1, psi 2. So this is two-way degenerate here. So if the Hamiltonian of psi 1 is equal to the energy level 1 of psi 1, and the Hamiltonian of psi 2 is equal to the same energy 1 of psi 2, in other words, these two wave functions have the same energy, energy 1, then you can do a linear combination of those. You can take the Hamiltonian of any constant C1 times psi 1, plus another constant C2 times psi 2, and that's going to be equal to the same energy of that whole quantity, same constant C1 times psi 1, plus this same constant C2 times psi 2. So this is a linear combination of those two energy levels. And you can do it 3, 4, 5, etc. more ways. You just have more constants, C3, C4, etc. Now, any linear combination will work for this. As long as, one, we already said those wave functions have to be the same energy level, and you have to normalize it. So all these constants, C1 squared plus C2 squared plus C3 squared all the way to Cn squared, have to be equal to 1 so that your function stays normalized. Now, it's not true though if you have wave functions that are at different energy levels. So let's say we have a Hamiltonian of psi 5 equal to energy level 5 times psi 5. And let's say we have Hamiltonian of psi 6 is equal to energy level 6 of psi 6 times psi 6. Well, we have two different energy levels here, energy level 5 and energy level 6. So if you try doing this linear combination here, you're not going to get the energy. Continuing on physical chemistry, chapter 19, we're back in section 3. Now we're talking about orbitals. Hopefully, if you're taking chemistry, you know what an electron orbital is by now. An orbital is a one-electron spatial wave function. All orbitals have this form of psi as a function of these three quantum numbers, n, l, and m. And you separate it into r, the radial function, which is a function of n and l, and then y, which is a function of L and M. Now the shape of an orbital is defined as its surface of constant probability density, which encompasses a large fraction or percentage, say 95%, of the probability of finding an electron. Continue on physical chemistry, chapter 19, we're in section 3. So now we're going to talk about real wave functions, namely p orbitals. So let's say we have our m is plus 1. This is our quantum number. So our orbital is 2 p plus 1. That's going to be equal to this constant b times e to the minus z. This is capital Z. So that's your quantum number. Times r, the radius, divided by 2a. Times r times sine of theta times e to the I phi. Now notice this is complex. This part over here is called our spherical harmonics. This is for our radius, obviously. So this constant b here, this is defined as 1 over 8 times the square root of pi times z over a to the 5 halves. Now again, this is capital Z here. So our 2p minus 1, m is minus 1 instead of plus 1, that's going to be equal to b times e to the minus z r over 2a times r sine theta times e phi. Now this here, notice both of these are complex. Now, r sine theta, you can, for rectangular coordinates, is x over cosine of phi, or phi. Now c, we're going to be using that in a bit. C is defined as 1 over the square root of pi times z over 2a to the 5 halves power. So our 2p naught orbital, 2p naught orbital is equal to c times e to the minus zr over 2a times r cosine theta is equal to 2pz. Now remember, and this is a real function, there's no I in this one. Now remember Euler's relationship, if you have e to the I phi, normally you learn it as theta, but it works for any variable. E to the I phi, that's cosine phi plus I sine phi. Hopefully if you took differential equations you'll learn that. So e to the minus I phi would be just cosine phi minus I sine phi. Continuing on physical chemistry, chapter 19, we're in section 3 still. So for the 2px orbital, we have 1 over the square root of 2 times the entire quantity of 2p minus 1 plus 2p plus 1. This is a real function, because we're talking about the spatial function for a real orbital now. This 1 over the square root of 2, this is a normalization constant. And remember this 2p, this is the name of the orbital. It's not 2 times p. So that 2 is not a number, a constant, or anything like that. And then, of course, the 2py orbital has to be perpendicular to the 2px orbital. And that's 1 over I times the square root of 2 times 2p minus 1 minus 2p plus 1. So you'll notice that 1 over the square root of 2 squared plus 1 over the square root of 2 squared, that's equal to 1. So this is a normalized, these are both normalized functions. So the 2px orbital, that's equal to the c times x times e to the minus zr over 2a. This is capital Z, remember, that's your, you know what I mean. Anyway, the atomic number. Anyway, c is equal to 1 over the square root of pi times z over a to the 5/2. Continuing on physical chemistry, chapter 19, section 3, we're talking about real wave functions. So our 1s function, the psi 1s function, is equal to 1 over the square root of pi times z over a to the 3/2 power times e to the minus zr over 2a. Now remember, we want to plot the square because the square is the probability distribution function. Now what we see here, so here we are, this is our psi 1s squared against radius. Notice it starts out really, really high over here and goes down. So the psi 1s squared is proportional to the radial function r squared. So from this, it seems like the electron, its most probable place is at radius equals 0, which would be the nucleus in the case of an atom, obviously. We're talking about atoms, electrons. Now that obviously interpretation is wrong. You're not going to find the electron in the nucleus of an atom. So why? Well, this is misleading because all we're doing right now, we're looking at the radial portion of this function. Instead, what we need to do is we need to take this and multiply by 4 pi r squared. I'll show you on the next slide why. But basically, this is the formula for a circle, or a sphere. So what we're doing is we need to analyze the sphere in 3 dimensions rather than a circle in 2 dimensions. It'll make more sense. Continuing on physical chemistry, chapter 19, section 3. So we're continuing on about real wave functions. So let's talk about a sphere within a sphere within a sphere, etc. So we have one radius, r, and then we have a slightly larger radius, so the difference is the differential of r. So the total radius would be r plus dr. So the volume of this outer shell is going to be 4/3 pi times this radius, which is r plus dr cubed. And then the volume of this inner shell is going to be just 4/3 pi r cubed. Now the difference between them two, after a little approximation, basically comes out to 4 pi r squared dr. So that's the factor we're going to multiply times that radial function we had on the previous slide. So now instead of just graphing the probability psi 1s squared, we have 4 pi r squared times psi 1s squared. Now, as you can see, what happens, it starts at the origin, 0, 0, it goes up, and then it comes back down. So it has a peak height here. Now this turns out to be 0.529 angstroms for hydrogen. Now how do you find that? Well, hopefully when you took calculus, you know up at the top it's going to be flat. So the derivative is equal to 0. So you take this whole thing and set it equal to 0. So we have the derivative with respect to r, remember because we're in spherical coordinates, is equal to 4 pi r squared psi 1s squared equals 0. So you solve that, you just get r is equal to a over z. Now for a hydrogen atom, remember z is the atomic number, that's capital Z. Z is equal to 1, so r is just equal to a, which is 0.529 angstroms. Continuing on Physical Chemistry, Chapter 19, Section 3. Now we're going to talk about the average value, also known as the expectation value of a quantity. Now let's say we have any quantity m, and we want to find the average. You remember these brackets here, these mean average. I think we mentioned that before. So it's going to be the integral over all space of psi star of m hat, so the operator for this quantity, times psi d tau. Remember, d tau means the integral, this means integral over all space. So for, let's say, radius, the average value of r, we've got the integral from 0 to 2 pi for the phi angle, plus the, of the integral of 0 to pi for the theta angle, of the integral from 0 to infinity for radius, of psi star r hat, which is the operator for radius, of psi, times r squared dr sine theta d theta d phi. So for spherical coordinates, remember d tau, or d tau in rectangular coordinates, Cartesian coordinates, was just dx, dy, dz. But since we're in spherical coordinates now, d tau is going to be equal to all this, the r squared dr times sine theta d phi. Now, these spherical coordinates, oops, I meant coordinates. I think that should be spherical harmonics. But anyway, these are going to drop out since they're already normalized. So all this, it just simplifies to the average value of the radius is going to be the integral from 0 to infinity of psi star of r hat times psi times r squared dr. And to make it even easier, the r hat operator is just radius. So you can actually combine these and you'll get r cubed. Continue on Physical Chemistry, Chapter 19, we're in Section 3. So we're talking about how the spherical harmonics are normalized for any wave function. So let's talk about phi. Capital Phi, remember, is the function, lowercase phi is the angle. So for phi, we integrate from 0 to 2 pi. We take just phi squared because it's real, so we don't need a complex conjugate. That's going to be equal to 1. So the reason is, and then likewise the integral from 0 to pi of theta, this is a capital theta, the function, this is lowercase theta, the angle. Again, we have this absolute value of theta squared times sine theta d theta, that's equal to 1. So like for a 1s shell, the theta function is just 1 over 2 pi. So we integrate 0 to 2 pi of 1 over 2 pi d phi. Oops, did I screw that up? Should be d theta. Oh, that's weird. I screwed around the... Hold on a second. Okay, we're in Physical Chemistry, Chapter 19, Section 3. We're talking about how the spherical harmonics of a function are normalized. So for capital phi, remember, that's the function, lowercase phi is the angle. For that one, we integrate from 0 to 2 pi. And it's a real function, so its complex conjugate is just itself. So the integral from 0 to 2 pi of capital phi squared d phi, that's equal to 1. And likewise, the function capital theta and the angle lowercase theta, that one you do from 0 to pi. So the integral from 0 to pi of capital theta squared times sine theta d theta, that's equal to 1. Now for a 1s shell, capital phi is 1 over 2 pi. So we have the integral from 0 to 2 pi of 1 over 2 pi d phi. That's just going to be phi evaluated from 0 to 2 pi. So we get 1 over, oops, oh, the 1 over 2 pi disappeared. Oops. Okay, 1 over 2 pi times phi evaluated from 0 to 2 pi. So The 2 pi over 2 pi is going to cancel out, you get 1. Likewise, capital theta for 0, 0, that's our 1s orbital of theta, that's rad 2 over 2. We showed a few slides ago why that is. So the integral from 0 to pi of 2 over 4, because that's this squared, sine theta d theta, is 1/2 times the integral from 0 to pi of sine theta d theta. That's 1/2 times minus cosine theta evaluated from 0 to pi. So then that becomes 1/2 times minus cosine pi minus a negative, or just positive cosine 0. That gives you 1/2 times positive 1 plus 1. So we get 1/2 times 2, that simplifies to 1. So what that means, at least for a 1s orbital, that both phi and theta are normalized. And you'll just have to take my word for it, the rest of them are also. So remember, multiplying those two together, you get y, which is our, based on quantum number lowercase l, lowercase m. So it's a function of just theta and phi. This is called your spherical harmonics, and this is normalized. Continuing on physical, chapter 19, section 3. Now we already talked about this, but we're going to review it because we're going to expand on it with an example. So we're going to talk about the complete description of an orbital. Now remember, an orbital is a one electron spatial wave function. All orbitals, this is supposed to be an R, looks like an L. All orbitals have the form of psi based on the quantum numbers n, l, m is equal to the wave function r, the radial wave function, which is based on the quantum numbers n and l, times, this is supposed to be a y, not another psi. And that's the spherical wave function based on quantum numbers L and M. Now the shape of an orbital is defined as a surface of constant probability density that encompasses some large fraction of percent, say 95%, of the probability of finding an electron. Continue on physical chemistry, chapter 19, section 3. So here's an example. We have psi of a 2pz orbital. That function is 1 over 4 times 2 pi to the negative 1/2, so you could write this as 1 over rad 2 pi, times z over a to the 5/2, times r, times e to the minus z r over 2a cosine theta. Now, this is a graph of the actual function. So here's your x-axis, y would be in the plane like this, and then here's your z-axis. Notice it looks like a pair of identical circles. They're not touching unless, of course, you were to go to 100%. But this would be like 95% or something. So remember, when cosine is positive, then your angle is 0 to 90 degrees for theta. And when cosine is negative, then your angle is 90 degrees to 180 degrees for theta. And these are circles because of this cosine function up here. Now, if you graph the function squared, that's probability, remember. So again, here's your x, y plane, and then here's the z-axis. Notice it has the dumbbell shape that you're used to seeing for a p orbital, because this is the 2pz orbital. Continuing on physical chemistry, chapter 19, we're in section 5 now. We mentioned before how in quantum mechanics there's two different types of angular momentum. One of them is the orbital spin, which we've been talking about. Now we're going to talk about the electron spin. Now, as far as doing this, you need unpaired electrons. Now, you could just use pure monatomic hydrogen, but hydrogen is normally diatomic. Instead, scientists use silver. Silver, remember, is krypton plus 4s1 plus 4d10. So this one electron in the 4s shell, that's your unpaired electrons that is going to let you study the electron spin. So there is actually a fourth quantum number. Remember, so far we had n, l, and m. So we're going to have another one coming up, and that's for the electron's intrinsic spin. And this one is not an integer. Continuing on physical chemistry, chapter 19, section 5. So let's talk about some of the experimental evidence that there is such thing as electron spin or nuclear spin. These two things aren't the same thing, but they're similar. Obviously, we're going to be mostly talking about electron spin, because that's what comes interest to a chemist. So one is the Stern-Gerlach Experiment in 1921. This relates to hydrogen atoms through a magnetic field. 2, NMR and ESR spectroscopy. NMR stands for nuclear magnetic resonance. ESR stands for electron spin resonance. 3, the fine structure splitting of atomic spectra. 4, the degeneracy of excited states of atoms and molecules. And 5, the anomalous Zeeman effect, which relates to energy of an electron in a magnetic field. Continue on physical chemistry, chapter 19. We're in section 5. We're talking about electron spin now, which is orbital. The orbital electron angular momentum is similar. So for the orbital angular momentum, we had L, which is a vector, and the z component of L. So for L, well, the magnitude is just this lower quantum number L times L plus 1, square root of that times h bar. And remember, L is 0, 1, 2, 3, so it's quantized, obviously. That's why it's called quantum mechanic. And then the z component is Lz, and that's the z component of the angular momentum. And Lz is just m times h bar. And m is 0, plus or minus 1, plus or minus 2, all the way up to L. So now we can talk about the spin angular momentum. For this, instead of using L, we have capital S. And this 2 is a vector, and this 2 is going to have a z component. Now we're going to use, I'm writing a cursive lowercase s, so you know this lowercase, and then a regular print s for the capital S. So the magnitude of this s is going to be this lowercase s times lowercase s plus 1, square root of that times h bar. Now, here's the tricky part. We're going to see there's two types of particles. And lowercase s is going to go either from 0, 1, 2, 3, etc., or it's going to go 1/2, 3/2, 5/2. And I'll tell you later why that is and what this means. So this lowercase s here, this is called our spin angular quantum, angular momentum quantum number. So this is our fourth quantum number in addition to the m, l, and the n that we had before. So as an example then, let's say that we have a lowercase s, our spin angular quantum number is 1/2. Then m for that is going to be either plus 1/2 or minus 1/2. And so this sz, now we're capital S, the vector, the z component, that's going to be this ms times h bar. So remember this ms is going to go from minus s to minus s plus 1, minus s plus 2, etc., through 0 all the way to s minus 1 to s. Continue on physical chemistry, chapter 19, section 5. So remember, for the quantum number L, we had ml, which we simplified just m. Now for the lowercase s, the quantum number, we have ms, or just m. So for an electron, s is always 1/2. So ms can be 1/2 or negative 1/2. Now there are always two s plus 1 orientations for this. So you put, for an electron, you put in 2 times 1/2 plus 1, and you get two different orientations. Now the absolute value of s is just the lowercase s times lowercase s plus 1. So for an electron, you plug in 1/2 and 1/2, you get the square root of 3/4 h bar. So here we are, this is for an electron obviously, here's our z. So we have 1/2 h bar and minus 1/2 h bar. The length of this vector is what I just showed you, the square root of 3/4 h bar, and this corresponds to ms is 1/2, and this corresponds to ms is minus 1/2. All electrons have a spin of 1/2. This is your intrinsic spin, remember, not the orbital spin. Photons, on the other hand, they have a spin of 1, and that works out to ms is equal to plus 1/2 or positive 1 or negative 1. Which means either left or right circularly polarized light. Continuing on physical chemistry, chapter 19, we're finishing up section 5 now. So let's say this lowercase alpha, this is a spin function. So, and this alpha is a function of omega. This is a lowercase omega. Omega is a hypothetical internal coordinate. Read the book about that. It's just a mathematical tool. And then beta, this is another spin function. So beta is a function of omega also. Now remember, psi is a function of x, y, z. That was our spatial wave function. Now we're going to take psi 1s times alpha, and that'll give us our 1s alpha. Or we'll take psi of 1s times beta, and that'll give us our 1s beta. And this combined, this is our spin orbital wave function. Continuing on physical chemistry, chapter 19, we're section 6 now. So we've been talking about electrons and the hydrogen atom. Now we're going to talk about the helium atom and the Pauli principle. So this is a simplified diagram of a hydrogen or a helium atom at any one time. So you have electron 1 somewhere, you have electron 2 somewhere else, and then the third location, you have the nucleus, which has this other charge, Z times Z. Z would be 2 in the case of helium, obviously. So you have these three distances. You have R1, which is the distance from the nucleus to electron 1. You have R2, which is the distance from the nucleus to electron 2. And you have R12, which is the distance between the two electrons. Now, this is going to give us three different potentials. So the Hamiltonian for this, we have minus h bar squared over 2me, that's the mass of an electron, del 1 squared, minus h bar squared over 2me del 2 squared, minus z times e prime squared divided by r, oops, this should be r1, okay, minus z times e prime squared over r2, plus e prime squared over r12. So remember, the total energy is the kinetic energy plus the potential energy. This here is the kinetic energy for electron 1. This here is the kinetic energy for electron 2. Now we use the mass of an electron. Technically it should be mu for the, oh now I can't think of what it's called, the reduced mass. But remember, we showed that the reduced mass of an electron and just the actual mass of an electron is almost the same at 3 significant digits. So this is close enough. So remember, if you have a positive potential energy, oops, did I write that backwards? Yeah. So if you have a positive potential energy, that's repulsion. This is repulsion because both electrons have the same charge and they'll repel each other. Then you have negative potential energy, that means attraction. So this is attraction here, this is attraction here, because the electron and the nucleus have opposite charges. And like I said before, these first two terms, this is kinetic energy of the two electrons moving around. We're going to assume the nucleus is holding still because of, we're not talking about the atom moving as a whole, we're talking about just the electron orbits. And then the last three terms, these are the potential energy from the electrons orbiting or just being near each other in the nucleus. Continuing on physical chemistry, chapter 19, section 6. So because of that term R12, so the electron 1 and 2, we can't separate the variables to get an actual answer, a solution to that. So we can't get an exact answer. What we're going to do, we have different approximation methods. Now remember, using the Pythagorean theorem twice, the radius 1 is just equal to x1 squared plus y1 squared plus z1 squared, square root of that. Likewise, the Hamiltonian of psi is equal to energy times psi. Remember, though, we're using the psi for helium, not for hydrogen. So if you're going to actually plug it in and get an answer, make sure you pay attention and use the correct psi. Now, remember, psi before with hydrogen was a function of just x, y, and z. But now we have two electrons. So we have x1, y1, z1. That's the x, y, z for electron 1. And then we have x2, y2, z2. That's the x, y, z for electron 2. So psi is a function of 6 variables now. And remember, though, psi is a function of the spatial coordinates only. We have the separate function for the spin momentum. Now, in spherical coordinates, though, this is in Cartesian coordinates, obviously. In spherical coordinates, you could write it the same thing. You have R1, theta 1, and phi 1, that's for electron 1, and then R2, theta 2, phi 2 for electron 2. Now what we're going to do now, as an approximation, we're going to just cheat. We're going to ignore that last term. So we're going to just take that e prime squared over R1, 2 and get rid of it to simplify. On the next slide, I'll show you what happens when you do that. Continue on physical chemistry, chapter 19, section 6. So, continuing the approximation we were making, we're going to ignore the interactions between the two electrons of a helium atom. We're just going to say the Hamiltonian is just equal to the Hamiltonian of electron 1 plus the Hamiltonian of electron 2. So again, we're just assuming that the electrons do not interact. Then the Hamiltonian for electron 1 is going to be the kinetic energy for electron 1 plus the potential energy for electron 1. And likewise, the Hamiltonian for electron 2 is just going to be the kinetic energy for electron 2 plus the potential energy for electron 2. And so there was that fifth term that we're just going to blatantly ignore. So those can be solved exactly just like we did before, with the Hamiltonian of psi is equal to energy times psi for electron 1, and likewise the Hamiltonian of psi is equal to the energy times psi of electron 2. Now we're going to use the hydrogen-like atom approximation for each electron in helium atom, and we're going to say, okay, the energy 1 is going to be minus z squared over n squared times 13.6 electron volts. Remember, for helium, z is equal to 2, so z squared is going to be equal to 4. So the energy level for electron 1 is going to be minus 4 over 1 times 13.6 electron volts, which is minus 54.6 electron volts. And then the electron 2 will have the exact same amount. They're both identical. So the total energy is just going to be the sum of those two, which is minus 108.8 electron volts. Now the sad part is that's about 38% error, which is obviously gigantic. I don't even think that's one significant digit. So that's pretty big error. Continue on physical chemistry, chapter 19, section 4. So we showed on the previous slide for a helium atom what we expected the energy levels of the electrons to be. Now we can also do that experimentally to see how close we are. So if you go from helium to helium plus ion by removing an electron, that's called the first ionization energy. It's abbreviated IE2, that's not Internet Explorer obviously, or IE1 for the first ionization energy. And that's actually just 24.6 electron volts, which is less than what we estimated it when we assumed that the two electrons didn't interact with each other. And then taking that helium plus ion, removing the second electron to get a helium 2 plus ion by removing the second electron, that's called the second ionization energy. And that's the 54.4 electron volts that we estimated before. So the total ionization energy for helium is just 79.0 electron volts. So our percent error would be just subtracting the two and dividing, and that is where we got the 38% that we mentioned on the previous slide. So what we'd say then is that the ground state energy for helium is minus 79.0 electron volts. Continuing on physical chemistry, chapter 19, section 4. So I mentioned before already that for a helium atom, with those two electrons and they're interacting, we can't get an exact solution because of this term here for the potential energy. This is E prime squared over the radius 1, 2. Remember, this is R1, 2 is the distance between electron 1 and 2, and then E is just the charge of an electron squared in the CGS units. So this is the potential because of the interaction. So what we're going to do is use an approximation method. Talked about the perturbation method already. So we're going to abbreviate approximate with APP and then ground state with GS. So we're going to have this psi for the ground state, approximate, which is roughly equal to this whole thing here. So we have z over a naught to the 3/2 times pi to the minus 1/2 times e to the minus z times r1 over a naught, and then times z over a naught to the 3/2 times pi to the minus 1/2 times e to the minus z times r2 divided by a naught. And remember, z equals 2 for helium, of course. Continue on physical chemistry, chapter 19. We're actually in section 6. I said we were in 4. I don't know how I lost track of that. But anyway, so we're going to say then, that, remember the energy at the ground state is going to be the integral of the complex conjugate of psi at the ground state times the Hamiltonian of the wave function psi at the ground state with respect to tau. Remember, tau means all space. So we're going to use this z, say z is roughly equal to zeta, and zeta is going to be a refinable parameter. Now remember, this z, this is the atomic number. So this refinable parameter, this is going to be the effective nuclear charge. So instead of 2 for helium, it might come out to 1.4 or something, slightly less. I'll explain why later. So remember, we're trying to find the energy of the ground state. We're going to use an approximation. So we're going to put in the Hamiltonian of psi ground state using the approximation, and hopefully it's equal to the energy of the ground state times the psi at the ground wave function of the ground state. So see here that we're approximating now to hopefully get the correct energy for the ground state. Now for helium, remember, we have the psi ground state is roughly equal to just the 1s shell for electron 1 times the 1s shell for electron 2. So we have these two wave functions, and we just multiply them together. Now remember, we also write helium as 1s2, which is the same as writing it 1s1 times 1s2. Continue on physical chemistry, chapter 19, section 6. Now let's talk about two electron spin functions. Now, look, I made a list of possibilities here. We're going to talk about what it means. So we're just going to say for now that alpha is an upspin function and beta is a downspin function. So it's possible that we have alpha 1, alpha 2, which means that electron 1 is up and electron 2 is up. Or we have beta 1, beta 2, which means electron 1 is down and electron 2 is down. Now this is good form, and both of these are symmetric, meaning the electrons go the same way. Now, here we also have alpha 1, beta 2, which means electron 1 is up, and electron 2 is down. And we have beta 1 and alpha 2, which means electron 1 is down, and electron 1 is up. This does not work, because it distinguishes the electrons. You'll notice in both cases we have one electron up, one electron down. So this is really one possibility, because electrons are all identical. I mean, we've been calling it electron 1, electron 2, and keeping track of them, but that's not always a good habit, because like I said, they're all identical. Electrons are indistinguishable, so this bottom row, this is no good. Instead, what we're going to do is we're going to take a linear combination of this, and we're going to linearize it. And then that is actually the third choice, in addition to these first two. Continue on physical chemistry, chapter 19.6, where I'm talking about the two electrons of a helium atom. So we made this wave function, 1 over the square root of 2, this is our normalization constant, times alpha 1 beta 2 plus beta 1 alpha 2. This one is symmetric, which means if you switch around the electrons, the polarity is going to stay the same. And then this is 1 over the square root of 2, alpha 1 beta 2 minus beta 1 alpha 2. This one's anti-symmetric. That means if you switch around the two electrons, you'll change the sign. Let me explain why. So let's take this whole function again. It's the same one, you'll notice. We'll just call that A for now, to simplify. Now we're going to swap the electrons. So see here where we had a 1, we've got a 2. Here we had a 2, we got a 1. Here we got a 1, we got a 2. Here we got a 2, we got a 1. So this is the exact same function as A. All we did was swap the two electrons. So if we do a little bit of algebra, we pull out a minus sign, we get minus 1 over the square root of 2 times beta 2 alpha 1 minus alpha 2 beta 1. Notice this is equal to the original function A. So that means after we swap the electrons, it's all equal to minus A. So when you interchange the electrons like that, and it changes the sign, that means it's anti-symmetric, which is what we wanted. Continue on physical chemistry, chapter 19, section 6. Now let's talk about the Pauli principle. Now we have two kinds of particles to talk about. One is a fermion. A fermion is a particle that has a half integral spin, such as 1/2, 3/2, 5/2, etc. Example of fermions are protons, neutrons, electrons, or you can even count the entire nucleus of an atom as one big particle, and even if you do that, it'll still be a fermion. A boson is a particle that has an integral spin. So S can be 0, 1, 2, 3. This is lowercase s for the intrinsic spin quantum number, remember. For example, I already mentioned before that a photon has spin of 1. Now, the Pauli principle says if you have two identical particles, okay, we're not talking about an electron and a proton, either two protons or two electrons, two nuclei, whatever, but two identical particles, and you interchange them, then the total wave function, remember that it includes the spatial part and the spin part, is going to change to the minus function. In other words, it's antisymmetric if those particles are fermions, or they're going to just stay the same, positive side, which means it's symmetric if they are bosons. That's why on the previous slide I showed you the difference between symmetric and antisymmetric. Continuing on physical chemistry, chapter 19, we're in section 6. So now we're going to talk about the approximate ground state spatial function. Now it's 1s1, 1s2 for helium. Remember that's symmetric. So we say the psi for ground state is roughly equal to 1s1 plus 1s2. And then times 1 over the square root of 2, all that times alpha 1 beta 2 minus beta 1 alpha 2. Now this here, the wave function, is symmetric. But remember, it's a fermion, so the overall wave function has to be, I can't remember the word, but anyway, it's got to be overall antisymmetric. So if the wave function is symmetric, then it must be the spin function that's antisymmetric. So remember, you multiply the wave function by the spin function, you get the overall psi function. Now, this is another way to write this is just, spin up, spin down. Now we can also write that using determinants, or actually this is the matrix. So we have psi gs, ground state, so 1 over the square root of 2, that's our constant for normalization. So we have this whole matrix here. We have 1s1 alpha 1, 1s1 beta 1, 1s2 alpha 2, 1s2 beta 2. Now remember, for a 2 by 2 matrix, if we have the matrix of form A, B, C, D, the determinant is just AD minus BC. So if you were to do that here, this times this, minus this times that. Now for helium, remember, 1s2, that's our ground state. Continue on physical chemistry, chapter 19.6. So remember, we just showed about helium, the ground state, but what about the first excited state? Now you might think you could just increase the 1 to a 2, like a 1s1, 2s2, or a 1s2, 2s1, or 1s2, 2px2, instead of an s shell, a p shell. There's your x shell. 1s2, 2px1, or 1s1, 2py, instead of, an s shell or a px shell, py shell, or 1s2, 2py1, or 1s2, pz2, or 1s2, pz1. But this has the same problem we talked about before. This is keeping track of which electron is which we can't do because electrons are all identical. So instead, what we basically need to do is use linear combinations to generate the correct answer. So what we do end up for the first excited state, one psi function is just 1 over the square root of 2 times this whole linear combination, 1s1, 2s2, plus 1s2, 2s1. And then psi 2 would be 1 over square root of 2 times 1s2, 2s2, minus, should this be a 1? Oops, yes, that should be a 1. Okay. So you 1s1, 2s2, minus 1s2, 2s1. So that would be for your two different s shells, your two s shells. And then we have psi 3 would be 1 over the square root of 2 times 1s1, 2px2, plus 1s2, 2px1, and then psi 4 would be 1 over square root of 2 times 1s1 times 2px2 minus 1s2, 2px1. So this would be your pair of px shells. And then follow on the same pattern, you'll have your pair of py shells and then your pz shells. So that's 8 different wave functions for the next excited state for a helium atom. Continuing on physical chemistry, chapter 19.6. So I went ahead and did the other 4. So psi of phi should be 1 over the square root of 2 times 1s1 times 2py of 2 plus 1s2 times 2py of 1. And then psi of 6 should be 1 over the square root of 2 times 1s1 times 2py of 2 minus 1s2 times 2py of 1. And then psi of 7 should be 1 over the square root of 2 times 1s1 2pz of 2 plus 1s2 2pz of 1. And then psi of 8 should be 1 over the square root of 2 times 1s1 times 2pz of 2 minus 1s2 2pz of 1. Now, coming back to energy, remember what we're trying to do is find the energy levels of the electrons in the helium atom and so on. So we have the Hamiltonian of psi of k is equal to energy k times psi of k. So we're talking about k here, the state k. So like Ek is the energy of state k, psi of k would be the psi function for the state k and so on. So Ek is going to be the integral of psi star k times the Hamiltonian of psi of k d tau. And then that's also going to be the integral of psi k star times the energy of state k times psi of k d tau. That's supposed to be a tau, not a t. You can pull out the energy because it's constant, so you get the energy as state k times the integral of psi of k star times psi of k d tau. That just equals Ek, because remember, this function is normalized, so the integral is going to be equal to 1. Continuing on physical chemistry, chapter 19, section 6. So now we're talking about the s orbital. We have the 1s, 2s orbital. So there's 2 possibilities for this. We can have the 1s, which is singlet state, which means there's no degeneracy. And that's 1 over the square root of 2 times 1s1, 2s2 plus 1s2, 2s1. Notice this is symmetric. So it goes with 1 over the square root of 2 times quantity alpha 1 beta 2 minus beta 1 alpha 2. The other possibility is the S3, or the triplet state, which is 3-fold degenerate. So that's minus 1 over the square root of 2 times 1s1, 2s2 minus 1s2, 2s1. That's antisymmetric, so that'll go with either of these. Either alpha 1, alpha 2, or 1 over the square root of 2 times alpha 1, beta 2 plus alpha 2, beta 1, or beta 1, beta 2. So you notice, since this is symmetric, it goes with this antisymmetric. This is wave spin. And then since this is antisymmetric, it goes with the symmetric. This is the wave, this is the spin. Continue on physical chemistry, chapter 19, section 6. So then for the 1s2p shell, we have this 1p state. That's just 1 over the square root of 2 times 1s1, 2px2 plus 1s2, 2px1. And we have this 3p state, which is 1 over the square root of 2 times 1s1, 2px2 minus 1s2, 2px1. So remember, the integral of psi of k star, the Hamiltonian of psi k d tau, is equal to the energy of k. Now, instead of energy levels, we call them terms, or term symbols. So like 1s and 3p, these are the terms. Now, in a multi-electron atom, the 2p is actually higher energy than 2s. Remember before with, I think it was hydrogen like atom, whatever, we showed that they were the same energy level. They were degenerate. But it turns out to the electron interaction, they're not really. Continuing on physical chemistry, chapter 19. This is the end of section 6 finally. So here we are. Spin functions for this triplet state for the P are alpha 1, alpha 2, or beta 1, beta 2, or 1 over the square root of 2 times alpha 1, beta 2 plus alpha 2, beta 1. In other words, the 3 symmetric spin functions. So these are each symmetric, and the 3p spatial wave function is antisymmetric. So therefore, the overall wave spin function is going to be antisymmetric, which of course it has to be because we're talking about a fermion. An electron is a fermion. So that's 9-way degenerate. We have 3-way degeneracy in X, 3-way degeneracy in Y, and 3-way degeneracy in Z. Likewise, the singlet state is also 3-way degenerate. Continuing on physical chemistry, chapter 19, we're in section 7 now. We're going to talk about the total orbital and spin angular momenta and Russell-Saunders coupling. Now, an electron, hopefully you noticed by now, it's got two motions inside of an atom. It's got the orbital and the spin. Now, both of these are types of angular momentum. We mentioned that before when we introduced angular momentum. So, lowercase l1, that's the orbital angular momentum for electron number 1. And then lowercase s1 is the spin angular momentum for electron number 1. And then lowercase l2 is the orbital angular momentum for electron number 2. And then lowercase s2 is the spin angular momentum for electron 2. So we're going to call capital L, that's the total angular momentum in an atom. And then capital S is going to be the total spin angular momentum in an atom. Now these are vectors, so the L is just lowercase l1 plus l2, etc. And then S vector is going to be just lowercase s1 plus s2, etc. So it can be more than 2 electrons, so we'll just use summation notation. So L is going to be the sum over I of lowercase l sub I. Remember, this arrow means a vector. And then same thing, the total S is going to be just the sum over I, lowercase s sub I. And then I would be just all the electrons. Continuing on physical chemistry, chapter 19, we're in section 7 now. So the symbol code for an orbital is determined by the value of capital L. So if capital L is equal to 0, then we use the symbol code S, which means S shell, not spin. Likewise, if capital L is 1, we use a capital P for a P shell. Or if capital L is equal to 2, we use capital D for a D shell. If capital L is equal to 3, then we use capital F for an F shell. Then capital L is equal to 4, then we use capital G for G shell. Or if capital L is equal to 5, then we just call it a capital H for the H shell, not confused with enthalpy or Hamiltonian, of course. So these are called the symbols for the orbital, or the code for the symbols, or term symbols, or whatever. So this S here, 3s, is supposed to be pronounced triplet S, because this is an S orbital in a triplet state. And this is from that code, remember, this S does not mean spin. Now, if S is equal to 0, now then 2s plus 1 is equal to 1, and we get a 1 singlet P state. So this is our S for spin. So if we write 2s plus 1L, so this is the generic symbol code, and this here is the multiplicity, or the degeneracy. So let's say we have the spins of 2 electrons, they're both plus 1/2, or they're both minus 1/2, then they add up to 1, and then 2s plus 1 is equal to 3, and you have a triplet state. But if they're antisymmetric, you have one that's in plus 1/2, one that's in minus 1/2, they add up to 0, then, 2s plus 1 is equal to 1. Continuing on physical chemistry, chapter 19, section 7. So for 1s2p, we have lowercase l equals 0 for s, l equals 1 for p. Capital L equals 0 plus 1, which is equal to 1, therefore p. So we have s is equal to 1/2 plus 1/2, which is equal to 1, therefore 2s plus 1 is equal to 3, so we have the triplet p state. And then for s equals minus 1/2 plus 1/2, that's equal to 0. So 2s plus 1 is equal to 1, and we get the singlet p. Now for s equals 0, remember ms is equal to 0, and therefore there's one possible spin function. And that's 1 over the square root of 2 times alpha 1 beta 2 minus beta 1 alpha 2. Now those vectors cancel, so s is equal to 0. You have one going to the right, one going to the left. S equals 0. Now for S is equal to 1, ms is equal to minus 1, 0, or 1. So for ms is equal to minus 1, you have the beta 1, beta 2. You're going to get minus 1 half, that's minus 1, which is symmetric, obviously. And for ms is equal to 0, that's the 1 over the square root of 2 times alpha 1, beta 2 plus beta 1, alpha 2. That's 1 half plus minus 1 half is equal to 0. That's symmetric too, obviously. And then for ms is equal to 1, we have alpha 1, alpha 2. And there you get positive 1 half plus positive 1 half is equal to 1. Also symmetric. Continuing on physical chemistry, chapter 19, section 7. Now we're talking about Hund's rules. There are 2 of them. So the first one says, of all the terms arising from a configuration, the one with the highest spin, oops, I spelled highest wrong, but anyway, the highest spin angular momentum will have the lowest energy. Thus, triplet states are lower than singlet states. Now the second rule, among the terms of a configuration with the same spin angular momentum, the term with the highest orbital angular momentum will have the lowest energy. So basically the energy of a triplet p state is less than the energy of a singlet d state, which is less than the energy of a singlet s state. Continuing on physical chemistry, chapter 19, we're beginning section 8 now. So now we're going to talk about many electron atoms, namely lithium, because it comes next, and the periodic table. So lithium, of course, has 3 protons, 3 electrons. It has neutrons too, of course, but that's irrelevant because we're talking about the electromagnetic force. So I drew it as sort of a rectangle, but again, that's sort of arbitrary just to keep it kind of neat up here. So we have the nucleus and then 1, 2, 3 electrons. So the nucleus, remember, has got the charge Z times the charge of the proton. And then, of course, we have electron 1, electron 2, electron 3. Now, the Hamiltonian is going to have 6 terms then for the energy. So out here we have the electrons between the electron and the energy between the electron and the nucleus. And then out here we have the energy due to the repulsion of the electrons. So the Hamiltonian is going to have 3 attractions, that's, like I said, between the nucleus and the electrons. And it's going to have 3 repulsions between the pairs of electrons. 1 to 2, 2 to 3, and 1 to 3. And then, of course, it's going to have the actual kinetic energy of the electrons moving around. These are potential energy, like I said. So this is what the Hamiltonian looks like. You've got E prime squared over R12 plus E prime squared over R13 plus E prime squared over R23. So these 3 are obviously the repulsions between electrons. And then you have minus Z times E prime squared over R1, minus Z times E prime squared over R2, minus Z times E prime squared over R3. These are obviously the attractions between the electrons and the nucleus. And then you had the H bar squared over 2m, this would be the mass of the electron, obviously, times the del operator squared for electron 1, del operator squared for electron 2, and del operator squared for electron 3. Oops, I forgot to mention too, remember with helium, to get this to work, we made the matrix and we solved it using a determinant. It turns out we got that only works because it had a pair of electrons. With lithium, we have 3 electrons. Making a matrix like that and finding the determinant is not going to help us any. Continue on physical chemistry, chapter 19, section 8. So let's say we have the 2p2, so that's going to split into triplet p, triplet d, triplet p, singlet d, and singlet s due to the electron-electron interaction. So for lowercase l equals 1, s equals 1 half plus 1 half is equal to 1. So we get 2s plus 1 is equal to 2 times 1 plus 1 is equal to 3. And we get a triplet state. And for p2, we get s is equal to 1 half minus 1 half is equal to 0. Now, like I said, if you have this 3p here, it's pronounced triplet p. I pronounced that wrong a couple of times, so I got to remind you here. So anyway, s is equal to 1 and l is equal to 1. So j, remember, is equal to l plus s. So we get 1 plus 1 is equal to 2. And that's our j max. Now the j min is the difference between l and s. Well, it's always positive or not negative. So absolute value of 1 minus 1 is equal to 0. So the total degeneracy, multiplicity, we get 2L plus 1 times 2S plus 1. So for triplet P, L is equal to 1, so 2 times 1 plus 1 is equal to 3. And S is equal to 1, so 2 times 1 plus 1 is equal to 3. So 3 times 3 is equal to 9. So it's 9-way degenerate. Continuing on physical chemistry, chapter 19, section 8. We're talking about the helium atom now. Or lithium atom, sorry. So the Hamiltonian, I already showed you, it's got 3 terms for kinetic energy, 1 for each electron. It's got 3 terms for potential energy that are attractive. This is between each electron and the nucleus. And then it's got 3 terms for potential energy that are repulsive. This is between the pairs of electrons. Now that's the exact Hamiltonian for lithium. Now the repulsions are what make it hard to solve. I mentioned that before when we were doing helium. So what we're going to do is going to have an approximation for the Hamiltonian, which is roughly equal to the Hamiltonian for electron 1 plus the Hamiltonian for electron 2 plus the Hamiltonian for electron 3. And remember, I already said before, APP, we're going to use that abbreviation to mean approximate. Now the wave function for that then, the psi for approximate would be just the psi for electron 1 times the psi for electron 2 times the psi for electron 3. So that's basically we're doing it hydrogen-like, which means 1 electron wave function. So we're kind of back to where the electrons didn't interact. So the psi ground state for now is 1s1 times 1s2 times 1s3. And we're using 1s because it's hydrogen-like. And of course, this is symmetric. Continuing on physical chemistry, chapter 19.8. Pauli says, including the spin, remember that it must be anti-symmetric. So the procedure we use for, well, these aren't related, but anyway, the procedure we use for helium, it won't work for lithium. Again, it's because we have 3 electrons now instead of just 2. So instead, we're going to need determinants. I misspoke before when I said we can't use determinants. We are, it's just going to be a little bit different. So let's say we have F, G, and H, and those are 3 spin orbital functions. This is temporary, don't memorize that. So if the antisymmetric psi is going to be 1 over the square root of 6 times F1G1H1, F2G2H2, F3G3H3. And notice the 6 comes from 3 factorial. Remember, this is just a normalization constant anyway. Okay, so this is called a Slater determinant, named after John Slater. Now, when we do the determinant, if you take linear algebra, you already know how this is going to be, but basically you're going to end up with negatives coming from the middle column there. Continuing on physical chemistry, chapter 19, section 8. So now we're talking about a lithium atom. We did this matrix here the same way as we did before, but putting in the actual functions here. So we have psi for the lithium atom is 1 over the square root of 6 times this entire matrix here. So we have 1s1 alpha 1, 1s2 alpha 2, 1s3 alpha 3, 1s1 beta 1, 1s2 beta 2, and 1s3 beta 3. And then for the next one, it's also going to have to be 1s1, 1s2, 1s3, but then the spin has to be alpha or beta. So we could put beta 1 here, beta 2 here, beta 3, or we could put alpha 1, alpha 2, alpha 3. But either way, it's going to work out exactly the same. It's going to be equal to 0, which is no good. Now, the reason it equals 0 is because these 2 columns are equal to each other. Anytime you have 2 rows equal to each other or 2 columns equal to each other in a matrix, the determinant is going to be equal to 0. And there's no getting away from that right now. So remember, now we have the Pauli exclusion principle. The Pauli exclusion principle says that no more than 1 electron can occupy a given spin orbital. It's a consequence of this. This matrix is showing these 2 these are both the same spin orbitals here. So we can't do that because it'll be equal to 0. Now remember, for an orbital, just the wave function, we had 3 quantum numbers, n, l, and m. And then for a spin orbital, we had 4 quantum numbers, the same n, l, and m, and then m sub s, where m sub s is either positive 1/2 or minus 1/2. Now what we need to do is change this 3rd column, because that's what's causing our problem there. So what we do is we get rid of this 1s, and instead we put in a 2s. So basically this is telling you what you already knew, that the 1s shell it only has room for 2 electrons. So this third electron has to be in the next shell, and that's going to be the 2s shell, the next orbital, whatever you want to call it. Continuing on physical chemistry, chapter 19, section 8. So lithium has 3 electrons. So we have 2 electrons in the 1s shell, 1 electron in the 2s shell. Now we want to derive the term symbol for the ground state here. Now when we do this, we're going to ignore any filled subshell, which in this case is the 1s shell, obviously. So we want to just look at this 2s1, this 2s shell with 1 electron in it. So like I said, this 2s1, it means we've got 1 electron in the 2s shell. Lowercase l is equal to 0 because it's an s shell. So capital L is equal to 0. So our code is S, because, well, which you probably guessed anyway. We're talking about S shell, duh. So lowercase s, of course, is 1/2. So capital S is 1/2. 2s plus 1 is equal to 2. So that means the multiplicity of this state is 2, which means we have a doublet state. So we say 2s, or S, actually it's doublet S, is the code for ground state lithium. Now, what is the degeneracy of that state? Well, remember, it's 2L plus 1 times 2S plus 1. So we get 2 times 0 plus 1 is 1. 2 times 1/2 plus 1 is equal to 2. So it's 2, which, well, it's a doublet state. Duh. That is all I got.